Your halogen molecules we know, halogens. They are generally in a molecular state exist. That is X2 like halogens. Okay. Now, your fluorine, chlorine, bromine, iodine, and astatine is a radioactive element. These are in a molecular state. Halogens these are. Here halogens, fluorine, fluorine, between there is one covalent bond is there. These two are the same. Like chlorine, chlorine covalent bond is there. Here bromine and bromine covalent bond, iodine and iodine also covalent bond is exist. Both are the same. That's why these are called a your homodiatomic molecules because here are two same type of atoms are present. Homodiatomic molecules. Now here heading is interhalogen compounds. Interhalogen compounds means here themselves combine with other halogens means here fluorine combines with chlorine or bromine or iodine I2. So the fluorine, chlorine or fluorine, bromine, fluorine, iodine like this. I form one type of compound that is like fluorine and chlorine like bromine and fluorine like iodine and the fluorine. These are also a halogens, but they are not the same. They are heterohalogens. Heterohalogens means different halogen atoms are present. That's why chlorine is different, halogen fluorine is different. That's why these interhalogen compounds are formed by the direct combination of halogens with another halogens. Like these are the compounds which are formed by combining themselves with the same group elements. So your halogens combine themselves with other halogens. Are known as interhalogen compounds. Simply halogens we know, but here interhalogen compounds. Inter means themselves combined with the same group elements with other halogens. They are generally XX-1. We know here halogens are denoted by X2 means two are the same. That's why we can take XX like. Between X and X there is even a covalent bond is there. Same here XX dash. Like XX dash 3 is there. Here XX dash 5 it is. XX dash 7, not more than that. Because in its outermost orbit in halogens, how many are there? Valence electrons? 7. That's why maximum it forms 7 covalent bonds. In this case, or whatever it, any case, here X dash, here X and X dash like these. These are simply halogens. These are interhalogen compounds. Now, your X and X may be same, but your X and X are not the same, differs. So, what is your X dash? In all the cases means, generally in this case, your X is equals to larger atomic size or atomic number halogen and less electronegative element. Here X indicates in this case, in all the cases, combination. Larger atomic size or the number halogen and less electronegative. X dash is small atomic size halogen, and if it is small, that is a high electronegative element. Clear concept here? XX dash concept here, we know. In all the cases, any combination, if you can take here, X is larger atomic size or less electronegative, X dash is small atomic size. Whenever small, high electronegativity is present. So here fluorine, chlorine, bromine iodine, when compared with chlorine, fluorine is small size and high electronegative. That's why while combining fluorine and chlorine, which is considered as the X dash fluorine. That's why this combination is, example is for this, example is ClF, here dash means this, ClF. In this ClF, X dash, see X is chlorine. Now in this case, ClF, in this case it is X dash. Because here X is compared to chlorine and fluorine, chlorine is more electronegative, more large atomic size element and less electronegative element, whereas fluorine is small atomic size and high electronegativity element. We can take a combination as like BREF. We can take combination IEF also we can take, because chlorine, bromine and iodine are the larger in size, this is small. We can take combination like here BRCl. See it, XX dash. This is the BR is larger atomic size, less electronegative than compared to chlorine. And here ICl also we can take, because compared to the chlorine, large atomic size. And finally, one more combination will get it, that is BR combination, that is IBR. So compared to iodine, bromine size is small, that is this is X dash. These are some important examples for X dash combination. Now here next one is X dash 3. Now this is always smaller in size. X dash is smaller in size. This is larger in size. That's why we can take ClF3, BrEF3, here IEF3 like. Or we can take BrCl3, ICl3 also we can take. While comparing these two, dash is always in a smaller atomic size. Smaller atomic size is nothing but high electronegativity element. Then for next one is X dash 5, that is ClF5, BrEF5 this is, here IEF5 this is. Now also we can take like BrCl3. Now here generally X dash 7, in this case we can take a ClEF7. So here ClEF7 like BrF7 and so on, like IEF7, very very important. This is IEF7 in first year in chemical bonding explained. Octet electronic configuration, to explain octet electronic configuration, around iodine 14 electrons are there. Do not obey any octet electronic configuration. Beyond 8 electrons are present. Now here in this case one important point is there is a large difference in their sizes. Your iodine and fluorine atomic size are large difference because fluorine, chlorine, bromine, iodine, top to bottom size increases. Top to bottom size increases. Now here in interhalogen compounds, atoms ratio also increases. See here, iodine is 1, fluorine is 7. This is a 1:7 ratio. Total number of atoms, how many are there here? Total number of atoms are 8. 1 plus 7, 8. Means in these interhalogen compounds, the atomic size of these two halogen atoms, so size difference is more. The ratio of number of atoms present in that molecule also increases. So here there is a large difference in their atomic sizes, and it gives the more number of atoms interhalogen compounds. Number of atoms also increases. Finally, simple halogens we know, these are the interhalogens. Interhalogen compounds are the compounds, halogen compounds, which combine themselves with the other halogen atoms. The obtained compounds are known as interhalogen compounds, denoted as like XX dash examples, XX dash 3 example, XX dash 5 example, 7 examples. Here 1, 3, 5, 7 only, odd number only, because in its outermost orbit contain 7 valence electrons. By excitation, already given electron excitation in first excitation, second excitation, third excitation. Yeah, only one unpaired is there. It is first excitation, 3 unpairs are there. It is second excitation, 5 unpairs are there. It is third excited state, 7 unpairs are there. That's why this is ground state electronic configuration. This is the first excited state electronic configuration. This is the second excited state. This is the third excited state. Third excited state electronic configuration. Based on that, we'll get the different models. There are XX dash, XX dash 3, 5, 7. How it forms? What are the some important characteristics? Physical and chemical properties and structures we'll discuss. Very, very important. Okay. First introduction of interhalogen compounds completed. See, preparation methods. Preparation methods of interhalogen compounds. Generally, these are prepared by direct combination. Direct combination of formed by direct combination of different halogen atoms. Different halogens, different halogen atoms, and which are depends on some special conditions, conditions. Depending upon the conditions, we can prepare such a interhalogen compounds. For example, here direct your chlorine is reacted with fluorine. Now, fluorine directly react with chlorine, gives 2Cl here, like this is X dash model. If we can take like Cl2 plus F2, this is Xs, Here almost all equal volumes on heating. Now, if you can take some excess, here we'll get ClEF3. Now, here there are 2 moles. Now, Cl is balanced, but chlorine is 6. That's why I take 3 mole. That's why excess. Like Cl2 combines with 5EF2. Here also it is excess fluorine gas that gives 2ClEF5. This is. Now here the Cl2 plus 7EF2, it is also excess case on heating. That gives 2ClEF7. Like I2 combines with 7EF2, it gives in excess condition, it gives here the 2IF7. Very, very important this is. So in this manner, by using this chlorine combination, chlorine and iodine or bromine combination, to get the fluorinated compounds like interhalogen compounds, by using the volume, equal volumes or excess conditions, will get the corresponding interhalogen compounds like X dash model, it is X dash 3 model. It is X dash 5 model. It is X dash 7 model. So in this manner, we can prepare all different types of interhalogen compounds on the basis of some special conditions. Like your Br2 react with Cl2. Now it is in equal volume. It gives BrCl. Now here are 2 moles. Br series. Like I2 react with Cl2, it gives 2ICl. Like your Br2 react with Cl2, it is excess condition, it gives here the BrCl3. Now 2 moles. Take here the 3 moles. Like we can prepare by the direct combination of different halogen atoms, we'll get the different interhalogen compounds. Okay, among all these, at room temperature, ClF is a gaseous state. At room temperature means at 298 kelvins. Remaining almost all, based on their temperatures, based on conditions, exist as either a gas or liquid or a volatile solid in different colors. But at a room temperature, this is only gas. Remaining all are like these models are volatile solids as well as exist as liquids. Like this model XX3, X-5, X-7 are generally at this temperature, 298 kelvins. These models are volatile solids or the liquids, but this is in gaseous state at the temperature. So the temperature changes. Yeah, the special condition, experimental conditions, temperature, maybe pressure changes, their nature also changes. They exist either in a solid state or gaseous state or different depending upon the temperature conditions. But under this condition, all this is gas, remaining all models are the volatile solids, they are easily vaporizes as well as in a liquid state. Depending upon experimental conditions, exist as gases, volatile solids as well as liquids. Okay, some important physical and chemical properties of these interhalogen compounds. Here are properties of these XX dash model or maybe XX-3, XX-5, XX-7. All these are the different types of interhalogens. First one is all are colorless, generally colorless. depending upon the situation, either maybe a gas, volatile, solids, or liquids at 298 kelvins. Generally, they are covalent. They are covalent and diamagnetic. Covalent and diamagnetic in nature. Diamagnetic in nature they are. So the covalent means like X is there, halogens. Like fluorine is there. Fluorine and fluorine. Fluorine contains 7 valence electrons. Out of 7, 1 electron is bonded with another fluorine, and another fluorine also contribute 1 unpaired electron from its outermost orbit. It forms a sigma covalent bonds. Remaining 3 are the lone pair. All are paired. This is also paired. In this halogens, there is no unpaired electrons. Unpaired electrons. That's why it is a diamagnetic covalent. Similarly, X dash also like ClF is there. In this ClF, chlorine in its outermost orbit contains 7 valency electrons. Out of 7, 1 is donated to the fluorine. And the fluorine also, same family member, also contains 7 valence electrons. It also contribute equally, and equal sharing takes place. It forms one covalent bond like this. Leaves a dot structure. It is paired, no unpaired in outermost orbits. One covalent. All these are the paired. That's why these are also covalent and diamagnetic. Why it is a diamagnetic means unpaired electrons n valence is equals to 0. 0 electrons are present. Whereas in case of only fluorine atom, atomic number is 9, electronic configuration 1s2, 2s2, 2p, like here 5 is there, outermost orbits. Here are 2 electrons and here 5 electrons are there like this. Now it is 1 unpaired electron is there. Fluorine atoms are paramagnetic. Like fluorine molecule, like fluorine, one unpaired, mutual contribution, mutual sharing. It forms a sigma covalent bond. Remaining all are paired. All these are paired. So it is paired, all are paired. That's why in this molecule, the halogens or interhalogen compounds are covalent and diamagnetic in nature. Clear? It's general property like physical state and covalent and diamagnetic in nature. Next one is solubility. Solubility of these interhalogen compounds. And reactivity of interhalogen compounds. Generally, here X dash interhalogen compounds are generally having intermediate physical properties as halogens. Halogens X, these are. Here X dash and X, these are the interhalogens and halogens. Their properties are intermediate, but their physical properties like boiling point and melting points are somewhat greater or more melting and boiling points more than X and X. only this is one there means your boiling melting points of interhalogen compounds somewhat more than normal halogens, because your atomic number or atomic mass of these interhalogenic compounds are not say varied, their melting and boiling points increases. Remaining physical properties are intermediate between interhalogens and halogen compounds. Then here reactivity of these interhalogen compounds. Reactivity of X and X dash. Generally, here generally X and X dash are more reactive than X and X, except fluorine F2. This is very, very important. Except fluorine is nothing but here among fluorine, chlorine, bromine and iodine, among these four, more electronegativity element is fluorine. That's why electronegativity is more, and bond dissociation energy between fluorine and fluorine due to the low bond energy, bond dissociation energy. This fluorine-fluorine reactivity is more, already given while explaining the reactivity of normal halogens. Fluorine is more reactive than compared to chlorine, bromine and iodine. Similarly, in interhalogens also, X and X dash are more reactive than compared to X and X, like ClF is more reactive than compared to the Cl2, not F2. So are they comparing the all interhalogens and halogens, which is more reactive? F2 is more reactive. That's why generally X and X dash are more reactive than compared to X. X means except these remaining all halogens, so reactivity is less. That's why ClF is more reactive. Reactive order. Reactivity order is like ClF means X and X dash is greater than X and X, but not F2. That is, except that remaining fluorine, chlorine, bromine and iodine reactivity is less. Interhalogen compounds reactivity is more. Why are the fluorine is more reactive means this is between fluorine and fluorine, low bond dissociation energy. Due to the low bond dissociation energy, that is due to the inter-electronic repulsive forces. Inter-electronic repulsive forces. Due to the inter-electronic repulsive forces, bond dissociation energy, bond enthalpy is less, ready to break and ready to produce, ready to react with the other element. That's why fluorine reactivity is more. Why are the interhalogen compounds are more reactive than compared to the halogens, except fluorine? Give reason. 1 mark or 2 mark questions. Maybe they're asked based on this reactivity. Why are the interhalogens are more reactive than compared to the normal halogens, except fluorine? Give reason, like questions they'll create in a subjective examination. Your X and X dash are more reactive than X and X, except F and F, that is chlorine. Except this, remaining all interhalogen compounds are more reactive. Why? Give reason. Your X and X means like Cl and like F is there here. The size of chlorine is like big size, and it is bromine like year to year. So in interhalogen compounds, internuclear distance increases. Whenever internuclear distance increases, internuclear distance increases. Here bond dissociation energy. Bond dissociation energy, what happens? Decreases. When our bond dissociation energy decreases, reactivity increases. Reactivity increases because year-to-year length increases. Attraction decreases. They are ready to cleave, ready to produce, ready to participate in a chemical reaction. Whereas in this case, here the covalent bond nature. One more here, covalent bond strength decreases. Covalent bond strength decreases. Now reactivity increases. Reactivity increases. So due to these reasons, generally, yeah, interhalogen compounds are more reactive than compared to the normal halogens. Whenever these interhalogen compounds like X and X dash, like ClAf, or whatever it, any interhalogen compounds dissolved in water, they are readily soluble in water. Very, very important, soluble nature. So are the interhalogen compounds X dash, X dash 3, X dash 5, X dash 7, whatever it. So when like the models are dissolved in water, now I give the corresponding HF and HOCl. What is the name of HOCl? Hypochlorous acid. Chlorous, hypo nature. So among these Cl and F, in objective they will give the HCl and HOF. Also we can manage. But this is absolutely wrong according to the chemical property and experimental analysis. This is wrong products, wrong explanation. This is the correct analysis. Means when X dash model halogens when dissolved in water, lower atomic size elements gives halide ion, and higher atomic number or higher atomic size halogen gives a hypohalite ion, hypohalite ion. Very, very important. This is relation between X dash and water relation. Very, very important. Now, if it is reacted with X dash 3 is reacted with water, same combination here, same one like this. Halide ions, same. This is the common halide ion. Lower atomic size gives halide ion, but higher atomic size elements gives, but this combination gives like it gives halite ion. Halite ion. I'll give the examples. Don't worry. If it is X dash 5 is reacted with water, now same this combination, lower is common, that is halide ion. But here the lower is this. Higher halogen atoms gives a halate ion. If it is reacted with X dash 7 is reacted with water, H2O, now it gives lower is compulsory halide ion, but here higher atomic number halogen atoms gives a perhalate ion. We'll create one example for that. Very, very important relation. We'll create that. We'll we'll take one simple, only one model example to get different products. One is I'll take X dash. For this, I'll take ClAf is reacted with water. It gives HF plus HOCl. This is This is H plus and F minus. This is called a hydrogen fluoride ion. Hydrogen fluoride ion. Fluoride ion is nothing but a halide ion. This halide ion obtained by using like X dash, that is lower atomic size. Lower atomic size halogen gives halide ion. Like here it is a fluoride ion. But here the higher atomic number, this is the higher atomic number halogen atom gives you a hypothalamus acids. This hypothalamus acid ionized, it gives H plus plus OCl minus, like ClO minus. This ion is called a hypohalite ion. Halite ion. Now clear? X dash is reacted with the water. Lower atomic size element gives halogen gives halide ion. Higher atomic number halogen atoms gives a hypohalite. This is the hypohalite, like NaClO. It is a sodium hypohalite. Clear first one? So when like X dash model is reacted with water, dissolved in water based on their conditions. In this interhalogen, which one is a lower atomic number element? That lower atomic number element gives always ions like a halide ion, that is a fluoride ion. Higher atomic number it gives corresponding hypohalite. Similarly, your X dash 3. For this example is ClF3 is reacted with water. It gives same. Similarly, HF it is hydrogen fluoride. Now 3 moles are there like this, 3 moles. Now it gives your HOClO like this. Now here the 2 moles required here. Now here the HOCl means here hydrogen fluoride is a lower atomic number F minus, but here the H plus ClO2 minus 1 is formed. This is a halite ion. Now this is we can take as NaClO2 sodium chloride. Sodium chloride ion, sodium chloride molecule is produced when your X dash is X dash 3 is reacted with the water. It gives corresponding like this. You are balancing fluorine atoms and oxidant like this. We can balance by using these number of molecules. By balancing this, one is halide ion, and here halite sodium chloride molecules are produced. Similarly, X dash 5 is reacted with water. ClF5 is reacted with water H2O. Same. Similarly, it gives corresponding hydrogen fluoride. But here the higher atomic number element gives HClO3. This is the chlorate. Here the chlorate ion, like perchlorous acid. Here the chlorous acid gives corresponding chlorate ion like ClO3 minus 1. Similarly, X dash 7 is reacted with F7 is reacted with water. It gives the same corresponding HF plus. Here the HClO4 is formed. This is the perchloric acid. Here also chloric acid. It is perchloric acid. Now that perchloric acid gives perchlorates. So these are four very important. When it is reacted with X dash is reacted with water, it gives the corresponding halide ion and hypohalous acid. From that, we will get the corresponding hypohalites like halite ion. Second one is halite ion. Your third one is halate ion. This is the chloride, that is halate ion. Fourth one is perchlorate. Okay, there are very important four examples in chemical properties of interhalogen compounds. Based on this, I give the corresponding chloride ions or halide ions, hypohalites, halides, halate, perhalate. So we'll summarize, listen here. X dash with water H2O gives like I guess corresponding like halide ion plus hypohalite ion. So this halide ion is a lower atomic number halogen. This is the higher atomic number halogen. Next, X dash 3 with the water, same here halide ion plus it is a halite ion produces. Same, lower and higher. If it is X dash 5 reacted with the water, I gives corresponding halide ion, same, lower atomic number, higher one is halate ion, this is. Now here the X dash 7 plus water, it gives same, similarly halide ion plus perhalate ion. These are four important because in objective when like IF7 is reacted with water, what are the products obtained? Like a model they'll create. So in this IF7, which is lower atomic number halogen atom, halogen. That's why it gives HF plus, yeah, HiO4 is formed. It is very important. So to confuse the children in examination, they will give the HI also. HI plus HeFO4 also they will give. It doesn't forms like. Only fluorine forms only one oxo acid, that is HOF. That's why HF4 is not possible. That's why this combination is wrong. So IF7 is reacted with water, lower atomic number is halide ion, hydrogen fluoride, higher atomic number is corresponding product based on their combination, 1, 3, 5, 7 combination. It gives halite, hypohalite, halate, perhalate. This is periodate, HiO4. Like questions they will create in examination. Very important. So after this physical and chemical properties of interhalogen compounds, last one simple concept is there, that is structures of these different types of interhalogen compounds. So last one is important structures of interhalogen compounds. For example, here are type of interhalogen, like one important type this is. Like here X dash model this is. Here for these examples are like CLF, BRF, IEF. Also we can take like BRCL, ICL. Also we can take IBR. These are the examples of one type, that is X dash type this is. Once we can observe in this type X dash type, already given accept this CLF model at 298 kelvins. At 298 kelvins, here the CLAF is gas, remaining all are volatile solids or liquids. Volatile solids are liquids. So maximum based on this condition, physical state almost all same. Based on their condition changes, their gaseous or solid or volatile nature. But its structure is not defined here in this shape or the structure, because in this case, once we can observe the Cl bond F or Br bond F, anything we can observe it. Now in both the cases here, the chlorine in its outermost orbit contains 7 valence electron. Fluorine also contains 7 valence electrons in its outermost orbit. Out of 7, each one donate 1 electron to form a 1 covalent bond like this. So on each halogen atom, 3 lone pairs are there. Here also lone pairs are there. So generally there are so these are between Cl and F, there is when sigma covalent bond is formed. Now here lone pairs 3 are there, here also lone pairs 3 are there. So generally we can consider as a linear like hybridization. Once we can observe here in this case and in this case hybridization, here one sigma bond and 3 lone pairs we can take as sp3. sp3 is nothing but generally tetrahedral or pyramidal structure or angular, but here in this case, in all the cases, there is no structure like this, because here in both the cases are the same number of lone pairs, same repulsive forces are there, as linear shape is present, even though each atom undergo sp3 hybridization. So in experimentally spectroscopical experimental analysis, here structure is not designed in this case. Next one is X-3 this is. We can take like ClF3 like this, or we can take BrEF3, we can take IF3 this is, or here we can take BrCl3 or ICl3 are the examples for this. Same based on their conditions, based on their temperature condition, physical state changes. Orange color, red color, or solid, alpha, beta, like based on their condition changes allotropic forms. Here main important is the structure of these. Here central atom of element is chlorine, higher atomic number element is chlorine. That's why your central element is chlorine. Now here around the chlorine, here 7 valence electrons are there, but here 3 fluorine atoms are there, compulsory 3 unpairs required. First excitation takes place. That's why here two lone pairs. Out of these three lone pairs, one is exit, it forms like two unpaired, already one unpaired is there. Now, this is bonded with fluorine, this is bonded with fluorine, and this is bonded with fluorine. Now, between chlorine and fluorine, here the three sigma bonds are there. And here the lone pairs are 2 LP are there. Now finally, your hybrid orbitals are 2 plus 3, that is 5, nothing but sp3d. If it is sp3d, originally like trigonal bipyramidal structure originally. But due to the presence of this lone pair, and lone pair, bond pair repulsive forces, its geometry is T-shape or bent-like shape. T-shaped or bent-shaped structure it is. Not only here one CLF, all BRF3, IF3, all are having same T-shaped or bent-like shape, even though it containing a sp3d hybridization, this is. Okay, remaining two are there. X dash 5, X dash 7. I'll create, just listen here. One table I'll create. Next, your X dash 5 it is. For this CLF5 it is. Or BRF5, IEF5 like this. For this central atom of element like chlorine, around the chlorine 5 bonds required here. Out of 5, only one unpaired electron is present here, remaining 3 are the paired. That's why 4 required extra unpaired electrons, so second excitation takes place. That's why it contains only one lone pair. Remaining, these are the 4 unpaired electrons are present. Sorry, 5 unpaired electrons are present, like total 7 are there around chlorine. 1, 2, 3, 4, 5, 6, 7. Originally, this is one pair, this is one pair, this is one pair. 3 pairs and 1 unpaired is there. But here 5 sigma bonds required. That's why these 2 are excite. First excitation, second excitation. Now, with this chlorine, 1 fluorine atom is here. Here 1 fluorine. Now it is fluorine. Now it is fluorine, and here it is fluorine. Like it create like this structure. Now around this here 5 sigma bonds are there. 5 sigma bonds, and 1 LP is there. So the hybrid orbitals are here 1 plus 5, 6 are there, that is sp3d2. If it is sp3d2, its geometry is originally octahedral. It's not an octahedral structure. That is all these x-5 are the square pyramidal structure. Square pyramidal structure it is. Very, very important. Generally, by seeing this hybridization, sp3d2, its geometry is octahedral, but not octahedral. Its geometry is a square pyramidal structure. Like square pyramids are present like this. 5 sigma bonds are there here. 5 sigma bonds. So due to the presence of lone pair and bond pair here, and lone pair and bond pair repulsions, their bond angle and geometry also distorted, changes. octahedral to a square pyramidal structure. Then next one is like X dash 7 model, like IF7 is the best example. Some models are there, stable molecule is IF7. In this iodine is central atom of an element. Originally 7 valence electrons are there. We want 7 valency electrons, like 7 valence electrons, 1, 2, 3, 4, 5, 6, 7. Means out of 7, only 1 electron is in ground state, single electron, remaining all are paired, 1 pair, 2 pairs, 3 pairs. But around iodine, 7 sigma covalent bonds required. That's why it takes place to a third excited state. So the third excited state required. Third excited state required. That's why 7 unpaired electrons are there here. 7 unpaired electrons are present in this. Now, each unpaired electron is reacted with fluorine. Here it is fluorine. It is fluorine. Here fluorine. Like fluorine. Here it is fluorine and it is fluorine. Around iodine, total 7 plus 7, 14 electrons are there. Do not obvious octet electronic configuration. Here the sigma bonds are finally 7 sigma bonds are there. So here the hybrid orbitals are sp3d3 like. So its geometry is pentagonal bipyramidal structure. Bipyramidal structure it is. Very, very important. These are some important points about the interhalogen compounds. So are the interhalogen compounds, some important models and their properties, examples and structures of some important interhalogen compounds. For all these interhalogen compounds, limited uses are there. Uses of XX dash or XX dash 3 like whatever it uses. So these are used as non-aqueous solvents. These are. And these are used as a fluorinating agents. Fluorinating agents. So here to enrich uranium from plants, your uranium is reacted with ClF3 like 2 moles, it gives UF6 plus Cl2 gas is liberated. Uranium hexafluoride. These are the some important uses of interhalogen compounds. Finally, about interhalogen compounds, preparation methods, properties, physical and chemical properties, and solubility main important, structures important, uses also very, very important. Regularly in objective they'll ask one question that is what are interhalogen compounds? Give an example. Why interhalogen compounds are more reactive than compared to normal halogens? Give reasoning. All the points covered, almost all points covered. Remaining only one simple concept is there in P block elements. Tomorrow we'll start, that is 18th group elements. Very simple concepts.